All right, let's finish up lesson 10, error handling and debugging, by going through the gradient descent algorithm. We're going to add a couple of things to our gradient function that we created last time, but we'll do that together. Okay, so what the gradient descent algorithm is trying to do is find a minimum. And so the way that you do that is you start off at some place, right? You see this x0 here, right? So this is some x0. And then all we want to do is we want to move it. So all the gradient does is give us the direction. We're going to move in this direction. So the gradient could be huge. It could, I mean, depending on what these numbers are, and when you substitute them in, the gradient could point way out here somewhere. So that's why we end up using this alpha term in order to size the gradient. In other words, we don't want to take, because in reality, the derivative are all very local measures, and you don't want to jump too far in the direction, in some direction that that's a local measure. So that's the idea. We want to make some alpha small. You know, it could be 0.1, 0.2. It could be 1. It could be 2. I mean, it just sort of depends on the function and how quickly the algorithm is going to take you to the minimum. You can find out very quickly if the gradient descent is actually descending by just comparing the function values, right? So if f of x0 should be smaller than f of x1, which should be smaller than f of x2, if your alpha is correct. If alpha is too, I shouldn't say correct, if it's small enough, if alpha is small enough. If alpha is too big, you could possibly take a step way over here that's worse off than where you started from, and then, oh, by the way, it's going to point back this way, and it's probably going to take you a step, and you're just going to keep going further and further and further away from the minimum. So that's the idea. We want to find the min, and we can take maximum problems and multiply by -1 in order to find and also find the maximum problems using this. But in general, in the nonlinear optimization world, generally you look for the minimum, and then you just, if you have an objective function, if you want to max it, then you just multiply it by negative and find the minimum of that. Okay, so the idea is start at x0, and then x1 will be wherever your previous one was plus alpha times this gradient at x0. So if you look at the orange or the peach little color here, that's the direction of the negative gradient, and it starts at x0, and this would be x1. And we can write that if you really want to see it. So this would be x1, this one would be x2, this one would be x3. And what happens, what ends up happening is this gradient gets smaller and smaller. Now I did not denote that, but it's very incrementally smaller on the way here. But what happens is at the minimum, if this is my minimum right here, then the cool thing is that the gradient at the x star, right, where x star is the min, is equal to 0, right? So you take the partial derivative, set them equal to 0, and that's really what how you find it if we're going to symbolically, or I shouldn't say symbolically, if we're going to analytically solve for this guy not numerically. This is the numerical version of basically doing the same thing. So this is what we're about to program. So we're going to go over here to Spider, and we're going to program this thing up. So let's jump over to Spider and start doing that. And so what I have is the code from the last couple videos, and we're going to add a couple things in. So I'm going to add some things in here. We're going to now change the number of decimals. So, and we're going to do a little try except in here just to make sure that this thing's always going to work. So num capital D, or num decimals is equal to 3. And then I want to put a try suite in here. Try. And then if we're able to do I'm going to put this one first. Control X. Enter, Control V. And we'll take this guy out. So we're going to put that one first. And then for I, let's see, that still is good. That's still good. These all still work. All right, and then we get done with this statement, and then before we get out of here, before we get out of this try statement, we want to put gradient is equal to, and we're going to do another list comprehension. I'm going to do a round the gradient down to num decimals. Actually, we're going to do it one step at a time. So that's why I had to do the list comprehension for I in range n. I think that should work. And then we want to put an except clause in here. So if this thing doesn't work, we want it to simply return the same thing that we did here. So gradient is equal to, I'm going to go ahead and put a round f of x, or a plus h minus f of a minus h all divided by 2 times h, and then num decimals. All right, so what is that saying? If it's not a, oh, I need to put in the error here. So the exception, so type error. This will be a type error if length is only one number, right? So if this is a single variable version, so this should be the derivative. That's basically what we're doing. If you put a single number in here, you just get the derivative out, and that's what this thing is estimating, and it's rounding it off to the correct variable. I'm sorry, not that one. This one. That's what this sucker's estimating. It's just estimating the single derivative. And then if that doesn't work, all right. So another except. It could be that maybe you didn't put in the right number, so your function and your a doesn't line up. So you got some other thing, and I'm going to just say print something to the effect of the input to the function is the wrong dimension, because it is possible that you could get something weird if you try to put like a two-dimensional vector into a function that so this function will do any dimensions, but eventually you're going to have to tell it the number of dimensions, and then if you put an a in here that doesn't line up, then basically this should be the error that comes out. And then we want to say, we want to pass out none in that case. And I think that's it. So let's run it. Grad f comma -5 2 and 3. So let's do console, restart kernel. We're going to restart the kernel here. And I'm going to run all this. And we don't need this test in here. I just typed it in from the last time. We know what this does. So -10, 2, 4, and 6. Look at that. So it looks kind of nice. And the reason why it's not 3 decimals is because when it ended up, it had all zeros, and so what it'll do is it'll chop off those zeros, and so that's fine. Okay. Because if you put 5.3, let's see what it does. 5.312. All right, so now you see that it's going down to the third decimal, because if it has zeros after this, it just chops it off, and that's why I wanted to put in a longer number. Okay, so we get something that's working here, and now we want to program the gradient descent. So let's start off with gradient underscore descent, and we want to pass in f x0, so where you want to start off, alpha, and we're going to go ahead and say alpha equal to 0.1 if it's not given. N is equal to, so this alpha and this n are sort of going to be commingled together. So in other words, if alpha is really, really small, then you want to give n a big giant number. But I'm going to just start off as 1,000, so that'll be a maximum that it gives to, and 1e to the -4. We'll say -10. The reason why this is going to be that because we want it to be really, really small. So I'm going to just let it be that guy. So let's start off with n is equal to length of x0. So x0. And let me put a bunch of spaces in there so we can start. So gradient is equal to gradient f of x0 of f comma x0. And then num, so I'm going to keep track of the number of steps that we actually take in order to go to do this thing. And then while, in general, I would do this in another function, but I just don't want to waste a bunch of time, so I'm just going to do this all at once in one step. So while sum, just sort of try to follow along with me, gradient I squared for I in range n. So what is that doing? It's squaring each term in the gradient vector. And then, and we're not taking, so we're just summing all those suckers together. And then I'm not taking the square root on top of that. That's one reason why this thing has to be really, really small. Because think about it, when you start getting small, you start squaring those 0.01s, you get 4 decimal places, and then you start adding them together without taking the square root back again, and that's just more computation. So that's why I just made this thing really, really small. As long as that, so that sum is greater than my tolerance, then I want to do this while loop. And while n is greater than, num steps. So num steps less than n, or the other way around, n is greater than num steps. So as long as this is true, it's going to still execute this while loop. And what is this while loop doing? We can click back over here. What is this while loop doing? Well, it's just simply updating the position. So if you start off at x0, well, I need to update this position. Well, how am I going to update this position? I'm just going to find the gradient, the new gradient, and then I'm going to multiply by alpha, and that's going to be my step, and I'm going to add it to that guy. And so you can see I should probably use a different, say maybe, I don't want to confuse people, so we'll just put in x equals x0, and then we'll say x is, and so that becomes our little, so x0 becomes where we start, and x is really keeping track of where we're at. I could call it x location if you wanted to, but x is equal to what? Well, we got to go in here and do x sub I minus alpha times gradient of I, because I've already calculated the gradient for that step. So we're just basically adding those two vectors. All we're trying to do here is just add two vectors together for I in range n. And so that's going to be your new x, right? So I started off by just saying, I don't have to do this. I could have used x0 in here, but I just don't want to confuse people. So I'm going to let x be my location. So x is current location, and then x0 is your initial location. And then what's the next thing we got to do? Well, it's going to come in and it's going to compare your gradient. Well, I haven't done anything with gradient yet, so this would be an infinite loop right now. Oh, actually, it would stop at n is equal to 1,000, but it's not really doing anything. You're going to sit at that, or you're going to be taking the same. You're going to be going in the same direction, but which is no good, right? Because your direction should update depending on where you're at. So remember what this thing looks like. When we got up in here, my direction should be different than when it was out here. So we need to calculate a gradient again. So gradient is equal to gradient f of f. I'm going to pass f in. I'm going to pass in x, and we'll just let h be that small number. And we will increment the number of steps that we take equals 1. And then we're basically done after that, because eventually this thing should return x comma num steps. All right, so let's find out what happens here. So gradient and we're going to have f is going to be my function. My initial point is going to be, I don't know, 2, 3, 4. No, we'll do 2, 3. Did we have one over here on this one? We didn't give it a spot, but we'll just let it be 2, 3. We know where this one goes. We know it goes to 0, 0. we'll let alpha at first be 0. I don't know, 3 maybe. We'll see what happens there. And tolerance, we'll just let it be that one. Okay, so let's highlight all this, F9, and it's going to 0.002. Okay, so it's going something really, really small in 11 steps. So let's do comma 10, longer. So 0.002, really, really small number, really, really small number. Let's take a bigger step. Oh, look at that. So it got there in, didn't tell me the number of steps. Oh, there it is, 7. So it got there in 7 steps. So 5. Looks like it got there in 1 step. Oh, it's probably because of the derivative. The derivative of this function is 2 times, and so 1/2 ends up being the exact right step. So that's probably not the 9. So it took us 7 steps, even though it's a bigger alpha. It just so happens that this one's not lining up exactly the way it should. And then F7 looks like it's going back up the number of steps anyway, 11. And then finally, I think this one will, yeah, this one gets away from us. So alpha is equal to 0.8, and if you saw the numbers, it's just going to be oscillating in between these two numbers, because 0.8 actually is the sort of the magic number for this particular function in this algorithm. 0.9, about 1, 2, 3. Oh, look, it gave us exactly the same thing we started off with. 1, 2. And look what happens. The bigger this alpha gets, the more chance you have of getting like out of whack. So in 44 steps, this thing is blowing up, and it should have went to 1,000, but there's probably some thing going on in here that causes some error in our numerical calculation. And that's why you see that, hey, it's coming back after 24 steps with these huge numbers, is because the alpha is too big. Remember that step. We don't want to take this local measure, this local direction, and then just take too big of a step. And then you take too big of a step, and you just keep, the further you get away from here, the bigger alpha is. I'm sorry, the bigger your gradient is, and the bigger your step's going to be. All right, well, that's all I got for this lesson. Just think about how we would incrementally do this sort of thing, right? So I showed you how I did it once I sort of figured it out, but we haven't really stepped through adding one line at a time, and that's generally how I program. So I didn't do that in this video. Maybe I'll do that for the next one. All right, that's all I got.